So last section in 7.2, we were saying that our differential equation was pretty simple, wasn't it? It was like dy dx is equal to k times y. So this means that the differential or the derivative is directly proportional to the dependent variable or directly proportional to y. And this is about as easy of a differential equation as you can get, because when you separate the variables, you get 1 over y dy equals k times dx. And we said if you take the antiderivative of both sides, you end up with y equals y sub 0 e to the kt power, which is just an exponential function. And I don't mean that as like an exponential function is easy to deal with, but the differential equation wasn't that difficult to solve. And we did, I think, 6 homework problems practicing that, did a bunch of questions in class, all that kind of stuff. So today, we're going to be challenged with some more difficult differential equations, but they're still going to be very doable. They're kind of entry level, if you will. They're not super sophisticated. So this one right here says that the rate at which the water leaks out is directly proportional to the square root of its depth. So they're telling us a rate, right? So it's like dy dt or dx, whatever you want to call it. I'm going to call it dt, is equal to, and it says that it is directly proportional. So that means that you're going to have a k value, but it's not just going to be k times y. It says that it's directly proportional to the square root of its depth. So you're going to have the square root of y right here. Okay, so write a differential equation that states the instantaneous rate of change of y with respect to t is directly proportional to the square root of y. Done. Now it says find the proportionality constant. Okay, so right up here it says that the rate, where is it here? At time 0, the depth is 12, and the rate at which it's leaking out is -3 centimeters per minute. So I'm going to put the -3 in for the rate. This one's a little different than we did in section 2, because we're finding one of the constants right now before we separate the variables and take the antiderivative. So that's kind of a little different, right? So I'm plugging the -3 in for the rate, and then I'm going to find my k value, and it says the height or the depth of the water is 12. So I'm plugging 12 in right there. So let's just put that down here. Y equals 12. It told me dy dt is -3, and I'm plugging those in. Plug in. Okay, and then find our k value. So our k is equal to -3 divided by the square root of 12. All right. So now it says solve the differential equation. Now, like I just said, this is a little different because we did part B first, and then we plugged in numbers to find our k back here on these problems, right? So a little different down here. Okay, so instead of using, I'm going to do what the book does. To be honest with you, I saw that in the book and I thought this is a good idea. Instead of using this, I'm just going to put the k back in its place where it belongs. So it belongs, just k right there. And so I'm going to move the square root of y to the left side. So I get 1 over the square root of y dy. And then here's what I was saying. Instead of putting -3 over square root of 12 right here, I'm just going to put the k back in because it just makes my life a little bit easier. Okay. Now we take the antiderivative of both sides. Okay. And then let's see, this is the same thing as y to the -1/2 power, right? That's the same thing as 1 over the square root of y. So if I raise the power by 1 and I divide by the new power, right? So if I take the antiderivative, okay, so I'm going to raise the power by 1. That would become y to the +1/2, and then I would divide by 1/2. Well, dividing by 1/2 is the same thing as multiplying by 2, so I just get 2 square root of y, right? Because the 1/2 power is the square root of y. So this side right here becomes 2 square root of y, and then the right side becomes k times t plus some constant. Now, I know we could have a c over here, but we said if there's a plus c here and a plus c here, we're going to move the constants all to one side of the equation, right? So it says solve the differential equation, find y as a function of t. Okay, well, right now it's not completely, solve for y. So what I'm going to do is I'm going to, divide both sides by 1/2, and I'm going to square both sides. Okay. So let's do that. And we also have some information. Doesn't it say at time equals 0, the depth, the y value is 12, right? So I could plug those numbers in. I could put 12 here, I could put 0 there, and I could find my c value. Let's do that right now. 2 before I solve for y. So I'm going to plug 12 for y, and then I'm going to plug 0 there, so I get k times 0 plus some constant. Okay, so my c value is equal to 2 square root of 12, right? Okay, so that's kind of important. And now what I'm going to do is I'm going to go back to this equation, and I'm going to try to solve it for y. So I'm going to move the 2 to the other side, so I get the square root of y equals 1/2 times the quantity kt plus c, okay? Then I'm going to square both sides, so I get y equals 1/2 kt plus, that's a t right there, t plus c, and then I'm squaring it. So let me put like brackets around this and square it, okay? Keep in mind my c value, I figured out what it is, and I have my k value back here, right? Here's my k value, and I'm going to plug that in as well. And now I'm going to go over to Desmos, and I'm going to show you what I put into Desmos, okay? So let's get Desmos right next to my work. I put in, let's see here. I put in, I did square the 1/2. I don't know why I did that. I guess I could change this back to a 1/2, and I could put a square bracket right here, and then I'd put a square bracket like right here. You know, if I'm trying to show, look, I'm getting exactly what I had right here. You notice I plugged in my k value was, where's my k value again? Yeah, -3 over square root 12. There it is right there. I could put the negative up with the 3 to make it look exactly like my work, but it doesn't matter. And then right down here, I put 2 square root of 12 for my c value, right? So there's my c value. And now when I'm plugging in k and c into my equation here, you know, the Desmos is doing it as accurately as possible rather than me trying to worry about decimals and everything, okay? It does say plot it. Okay, so let's look at that real quick in full screen mode. Here's my graph, you know, and the rate at which, or well, the amount of water, the height, I should say, the height in the can when it first started was 12, right? And then it leaks out, and you can see that the slope here is steeper here than it is down here, meaning the rate is getting slower, and it reaches a height of 0 after 8. Now, what was the unit again for our time? Let's see, where did it say here? In minutes? Is it in minutes? Where's the time? Minutes, right? So it says plot and sketch the graph. Consider the domain of t in which the function gives a reasonable answer. So when we think about that, we want to go between 0 and 8 minutes. Okay, so I'm going to say t is an element of the set where t is greater than or equal to 0 and less than or equal to 8. You might say, why is he being so fancy? I guess I could put just down, you know, interval notation, 0 to 8, right? Something like that. That's fine. I don't really care how you write it down, but that's our domain, right? And then I think there's a part D where it says, you know, how long does it take before it drains out, right? So at time 8, there's no water left, no water and no height, right? So that's how we're going to do these problems. In video 2, I'm going to kind of walk you through problem number 1. All right. Thanks for watching my video and setting up some notes. If you're not sure, like, what notes, what is he talking about? That's kind of what our notes are looking like right there. We're going to solve a differential equation that's a little bit more complicated than what we did in section 2, but not tremendously more complicated. We can handle this. Okay. Thanks for watching.